Hello, welcome back to Balanced Three-Phase Circuits. We're working on Y-delta problems. This is problem number 3. We're getting there. We're getting a little more complex each time we go along here. And this is not, again, I wouldn't consider it a full-blown problem, but it's definitely more complicated than the last one. So we're given the line-to-line voltage VAB at a balanced three-phase load is 4160 at an angle of 0 degrees. It's telling us the line current IAA is 69.28 at an angle of negative 10 degrees. And for now, just ignore part B. We're just going to focus on part A. Find the per phase impedance for a positive phase sequence. So there's a lot of information here. Again, positive phase sequence, that tells you something. And we're also given some information that we need to label on our diagram. So we're given VAB. Remember, that's a line-to-line voltage in a delta load, because A and B are the terminals of this triangle here, which is exactly the same thing as the line-to-line voltage, VAB. So that's something we're given in this guy. So let's go ahead and label a couple of things. Let's do it right here. So this is going to be, for instance, from here to here. That's going to be VAB, which is exactly the same as it is down here, right? We're given that as a known quantity. And then, let's see here, we're given this guy right here, this current, like this, I, little a, big A, and we're given that problem, or we're given that guy as 69.28, angle negative 10 degrees. This is amps. And what we're asked to find, so we're kind of deciphered the first, almost the first part of the problem, the line-to-line voltage, VAB, okay, that's given to us. We didn't write the number down over there, but we know where it is in the drawing. The line current AA is given by this for the A phase, and then it's asking for the per phase impedance. When it's asking for the per phase impedance, there's nothing else given, nothing else is talked about in this problem. The line impedance, the source impedance, none of that stuff is present. So when they talk about the per phase impedance, the only thing they possibly could be talking about is the impedances of the load, the triangle here, the delta. And if it's balanced, each of these are equal to one another. So when it says per phase, it means this is the impedance for per phase A, or for phase A, impedance for phase B, and impedance for phase C. So the per phase impedance is just Z delta. So we want to find Z delta. So how do we do that? Well, we know from basic circuit analysis that Z delta is just going to be the voltage across that impedance divided by the current going through the impedance. Okay, and we know the voltage across it because that's VAB, right? VAB is given as 4160 at an angle of 0. So we actually have this number. We know this number at the top. We know the voltage across this load, Z delta. But we don't know the current because the current is IAB, and that was not given in the problem statement. We were given IAA. Now you see why it's so important to draw a picture, because if you're just kind of given all these things and you don't really know what a line current and a phase current is and all that stuff, and you don't draw anything, you're going to be tempted to use this current and stick it in here and get the wrong answer. But this is not the current flowing through this load. This is the current coming in from the line direction. So what you need to do is convert, because we know the line current. We can then find the phase current by using our square root of 3 rule. That will give us this current, and then we'll have both pieces of information to find the load impedance Z delta. So that's going to be our strategy. So what we're going to do over here is we're going to say that IAA is equal to the square root of 3 times IAB at a phase shift of either negative or positive 30 degrees. And we go back to our problem statement, and it says, what does it say here? Balanced three-phase load, line current, per phase impedance for a positive phase sequence. So if it were a positive phase sequence, we pick the top one. Negative phase sequence, we pick the bottom one. So we're just going to erase this right now, and it's going to be at negative 30 degrees. So we're given this piece of information. That's the line current. We want this one. So let's go ahead and rearrange it just to kind of continue on here. So let's go ahead and put the phasor in here. 69.28 angle negative 10 is square root of 3 I capital AB negative 30 degrees. All right. Now we want to find out what this phase current is, IAB. And the easiest way to do that is 69.28 negative 10 divide by square root of 3. And we're dividing by this guy, so it's going to be negative 30 degrees. And you could stick this in your calculator exactly as it sits. just to make it a little more clear to match what you'll probably see in most of your textbooks, the way you will see this is 1 over square root of 3 times 69/28 angle negative 10. And this negative 30, we move it upstairs, actually becomes a positive 30. Right? So that's how you would typically see it in a book. That's why I'm kind of going through the trouble of showing you this. You could stick it in your calculator straight away. Notice what will happen. Negative 10 minus negative 30, that's what will happen when you do these. When you do it in the calculator, if you have a top and bottom, you'll be subtracting these exponent values, which means negative 10 minus negative 30, which means plus 30. That's what you have here. So you should get 20, either way you do it. So then IAB is going to be equal to, whenever you do all of this, you will get 40 at an angle of, like we said, 20 degrees. All right, but this wasn't the answer. This is the current flowing through this load impedance, and we know the voltage across this load impedance. So let's go back, or let's go forward, I should say, and let's find Z delta is equal to V over I. The voltage was given in the problem statement, 4160 angle 0. That's the voltage AB across that load. So 4160 angle 0. I is 40 angle 20. We just found that. Angle 20. That's the current flowing through the load. And so what you get for Z delta in polar form, depending on how your calculator is set up, you'll get 104 angle negative 20 ohms. We generally don't like to write impedances in polar form because we like to see the real and imaginary part. So if you just convert this to real and imaginary part, you'll get 97.73 minus J35.57 ohms. So this is the resistive part. This is a capacitive part because it's negative. This is what you get. So I'll probably circle this as my answer. So that is what you have inside this box. It's a capacitor and it's a resistor. And since it's balanced, the same impedance is present here, and the same exact impedance is basically there, because everything's balanced. All right, so that is the part A. Find the per phase impedance for a positive phase sequence. Now let's go to part B. Repeat everything for a negative phase sequence. Now you're thinking to yourself, oh, I have to go through all that again. But then you realize it's not hard because everything is the same, really. I mean, you want to know the current going through here, you want to know the voltage across it, and you divide the two. The voltage across it doesn't change because the voltage across that part of the load is exactly the same number, so the top number is the same. The bottom number, which is the current going through here, we calculated that using this rule because we did a phase shift. We chose the top sign here because it was in the first part of the problem, a positive phase sequence. This will then change for the second part of the problem. Try to resist the urge to go into your answer. If they say repeat for negative phase sequence, go to your answer and try to change it or something. Don't do that. You're going to miss a phase shift somewhere. You're going to forget something. It's better just to redo the calculation again. Even though it might be trivial, and you can go through here and you can probably see the answer, we're going to start with this again, but this is going to be different. That's going to lead to a new current flowing through that load. So it'll just take a second. So what we have is the relation IAA is the square root of 3 times IAB, and then it's either minus or plus 30 degrees. But in this part, it's a phase sequence which is negative, so we choose the bottom sign, right? And then we do exactly the same thing we did before. AA we found to be, or we were given actually, this guy, so we stick it over in the left. So it's going to be 69.28 angle negative 10, square root of 3, IAB, angle 30, positive 30, right? Then we're going to solve for IAB. So IAB, 69.28 angle negative 10, divide by the square root of 3, divide by the plus 30 degrees, okay, which is going to be 1 over the square root of 3 times 69.28 angle negative 10. All I'm doing is splitting out as a multiplication instead of as a division, basically. And then this is going to go upstairs and it's going to become negative 30. Right? So then I subtract these. What am I going to get? Negative 40 for the phase angle. Let me switch colors. Notice the magnitude is exactly the same because the square root of 3 factor is the same in both cases. So it's still going to be, let me double check myself here. It's still going to be I haven't even caught up just to make sure I've got everything right here. Negative 10, negative 30, yeah. So what we're going to get is we're going to get a magnitude of 40, same as before, but the phase angle is now going to be, you add these together, you get negative 40 for the phase angle. So the phase angle is totally different than before. So originally, see, the phase angle was 20 for this current. So if you start going to your answer and say, well, I'm just going to fiddle with the answer to get the phase sequence, you might get it right, but you're probably going to screw something up somewhere, and you need to make sure and have this phase angle correct. So this is the current, and now we'll recalculate Z delta. V over I, 4160, angle 0. And now we know that the current is 40 at an angle negative 40, like this. So Z delta, in this case, is 104, angle 40. Okay, we don't like to write them like that, so we typically convert to rectangular, 79.67 plus J, 6685 ohms. This is what I would typically circle. Now look at the interesting thing here. Just by changing the phase sequence, if everything else is true in the problem, I just changed the phase sequence, this is not capacitive anymore. This is a real part with an inductive part. So this is a resistor and an inductor, resistor and an inductor, resistor and an inductor, all the same, whereas before, the load that we got was capacitive because we had a negative imaginary part. So resist the urge, because you'll have this a lot. It'll say work the problem in a positive phase sequence, work it in a negative phase sequence. Don't go to your answers and start fiddling with that, because there's too many interrelations of, did you divide by the phase or did you multiply? Did you have the phase current, the line current? Is it phase shifted this way or that way? You start trying to add 30 degrees to something and you're just going to get confused. So go back to the first part and work it through again. Even though it takes a little extra paper, you're more likely to get the correct answer. So make sure you understand this, work it yourself. It's very important to get these things correct early on, because as we continue on, I mean, you've got the basic idea. Notice all of these problems are dealing with the load end. Why do you think that's the case? Because the source and the line end, we've done so many problems in the YY circuit cases that when we join these two things together, it's going to be trivial. Now that you know how to handle the load end over here, soon we're going to connect it to a line and a source, which is a Y source. And then at that point, the problem just becomes boring because you've done all the individual parts so many times. So follow me on to the next lesson. We'll continue going down that road in three-phase circuits.